So particles C and D collide on a frictionless surface. The mass of particle C is 4 times the mass of particle D. Alright. So the first bit we're going to do is look at the initial momentum of D. So I'm going to measure the distance there, and it actually comes out to 80 millimeters. And that's for 2 divisions. So therefore between each frame there's actually 40 millimeters. Okay. If I do the same one down here, but because they're small I'm going to count more divisions. 2, 3, 4, 5. Okay. So that comes out to 57 millimeters. And there was 5 divisions, so the distance between divisions is actually 11.4. However, C is 4 times more massive, so I'm going to times that by 4 and I end up with 45.6 millimeters. Alright, so on this side here that's the initial momentum, on this side here is the final momentum. So I'll do the same process here. I'll do 5 divisions, and it actually comes out to about 51 millimeters. I'll do 51.5 because I measured them before. I'm doing it fairly quickly here. So that comes out to 10.3. And because it's 4 times as massive, I'm going to times by 4, so that gives me 40. So that gives me 41.2. Alright, now I'm going to need to do the final one for D. So the distance between this point here is actually 92 millimeters. Divided by the 2 divisions, and that gives me 46 millimeters per division, and it has a relative mass 1, so I'm not going to times it by anything else. Alright, so we've now got the momentum magnitudes. Now we actually have to measure the angles, so I'm just going to swap it over down to here, and because the collision point is not very clear, what I'm going to do is a couple of parallel lines, because it doesn't really matter if you've got parallel lines, the angle doesn't change. So that crosses over here, line it up as best you can, and then I'll do another one over here, make sure they're parallel, and we then use the geoliner to actually measure the angles. Now I've done that before, okay, a little bit more carefully than what I'm quickly demonstrating to you here. So this angle in here is 12 degrees, this angle here is 17 degrees, this one in here is 16 degrees, and this one in here is actually 11 degrees. So let's actually go ahead and draw a vector diagram for this one. Alright, so I need to put in my reference line if I'm going to do a vector diagram. Doing this on a piece of graph paper is so much better practice, because then you can actually get the parallel lines nice and neatly. But if I can do it without graph paper, then you guys should be able to do it just as easily. Alright, so I'm going to be adding D first. So here's my starting point for my vector D, and the angle that it's actually shooting down at is 17 degrees. So I'm going to measure 17 degrees, line that up carefully with the starting point. So 10, 15, 17, and that needs to have a length of 40 millimeters. So just hold my pencil there, and that is 40 millimeters. Alright, now I'm just going to make another little parallel line here, so make sure they're equidistant. Just do it lightly, don't want it to block everything else. So now I need to add vector C at 11 degrees. So I'm just going to line it up there, 11 degrees. So 10, 11, so 10, 11 degrees. And it needs to have a length of 45.6, so 45.5. So just line it up, move that there, so 45 there. So this side here is the initial momentum. Alright, so now we need to check that one with the final momentum. So we're going over to this side now. So that one was D and then C. So we might as well start off with D again. So here's my starting point. I need an angle of 12 degrees. So carefully position that again. That study mate symbol blocks it off. So 12 degrees, 10, 11, 12. And that needs to have a length of 46 millimeters. So line it up there, 45, 46. Might be a good time for me to put on my glasses. Construct another little parallel line. You can see the line underneath it lines up nicely with the numbers. So I'll just use that as a guide. And now I'm going to draw C, and that's going to come down by 16 degrees. So I'll just position this here, line it up carefully, 10, 15, 16 degrees. And that length of the line needs to be 41. So line that up with there, 41 is here. And they're very close together. Okay, because I was doing it very quickly, you can see my previous one, it actually lines up even better. Okay, so I would say this one is conserved for momentum, that is. Okay, so let's have a look at the next one. So this one had so vector D came in with a magnitude of 40 and it dipped low at 17 degrees. Vector C was pointing upwards with a magnitude of 45.6 and it had an angle of 11 degrees. So the magnitude of the initial momentum was, we'll just go for 83 at minus 2 degrees. Alright, so let's now check it against the final momentum. So D had a final momentum of 46 and it bounced off at 12 degrees, and momentum C had a value of 41.2 and it dipped down at minus 16 degrees. Alright, so as you can see, the magnitude here was 80, we'll just make it a whole number, 85 at, and that's minus 1.2 degrees. So given that all the measurements were taken from the paper, again with the photocopy, very imprecise ruler, I think that's quite good. So yes, it shows that momentum is conserved.